All right, so we're going to start with chapter 16, which deals with conjugated systems. Conjugated pi systems, I should say. And so this really just deals with compounds that have multiple pi bonds oriented in a way in which they alternate double bond, single bond, double bond. And so we'll go through that in just a second, but let's look at this just from the context of looking at the types of dienes that we can imagine. So what is a diene? This is a compound with two double bonds. And so if I imagine a compound with two double bonds, there are really three ways in which I could arrange those two double bonds with respect to each other. So I could take a compound like this one where I have two double bonds like this, where the double bonds are separated from one another by one or more sp3 carbons. And so what we would call this type of system is a system known as an isolated diene system. So what that means is that the two carbon-carbon double bonds are separated from each other across space. The subject of this chapter is the second option, which would be a case where I have a double bond, a single bond, and then that second double bond comes right after that first one. So this system where you have the two double bonds on adjacent carbons, that's what we would call conjugated diene system. And this is the portion of this chapter that we're going to spend the most time on, is talking about these types of systems where we have alternating double and single bonds throughout a pi system. It does turn out that there will be a third way in which we could incorporate two double bonds into the same system, and it would be something that looks like this, where we actually have both double bonds in the system originating from the same central carbon, right? And so this is sort of a weird system. This is what we would call a cumulated diene. And these functional groups have a special name. These are actually called allenes. So this functional group is known as an allene. And this system is actually quite weird. We're not going to spend very much time on it other than to just talk briefly about what the orbitals look like. But this is a weird system because if you look at the earlier examples, the isolated and the conjugated diene, the carbons of the double bond behave just as exactly how you would expect, in that they're all four of those carbons are sp2 hybridized. And that's actually true for the conjugated diene as well, right? If you follow those rules that you remember from organic 1, that we have one pi bond at each of those carbons, so they're all sp2. Not quite the case with the cumulated diene. The two carbons on the end of that system are sp2 hybridized because they're each only involved in one pi bond. But that central carbon has two pi bonds, so it's actually an sp hybridized carbon, same as an alkyne, right? Because it actually has multiple pi bonds. So if you want to think about an orbital picture for a cumulated diene, it looks a tad on the weird side. So let's start with this carbon over here on the right. So if I think about how I would draw that system, remember that pi bond is made up of two overlapping p orbitals that are in phase. So we'll indicate the phases like this. And now if I want to think about coming up with a second double bond at that central carbon, I have to move the plane of that pi cloud perpendicular to this existing one, right? Because I don't have room to put in another p orbital in that same direction. So actually those pi orbitals are perpendicular to the ones that make the double bond on the right-hand side. Okay? And so what does that do for the hydrogens that come off of there? They're actually perpendicular also to the substituents on the first double bond. And let me change colors here just so we can clearly highlight what we're looking at. So this is the p orbital system. Do those in pink. So that's actually what's making those p orbitals form. That's sort of actually what's making the pi bonds form, I should say. And those interactions happen perpendicular to one another at the different carbons. So the big point here, don't worry too much about this, but the big point here is that allenes are a little bit weird. So their reactivity is quite different from other double bonds. So but the long and the short is we're not going to spend a whole lot of time talking about those. I want to now return sort of to the orbital pictures for the isolated diene versus the conjugated diene, and that really is going to drive home why the conjugated dienes are a bit different. So if I take a look at the isolated diene that I drew here, and I want to think about what those p orbitals look like on those two carbons to make the pi bond, I should imagine something like this, right? I have p orbitals that are interacting to make the pi bond on the left-hand side of the molecule, and then all the way over here on the right-hand side of the molecule, I've got two other p orbitals that are interacting similarly to make that pi bond, right? So this pi bond is here, and that pi bond is there. Now, what's weird about the diene is that because those two double bonds are right next to each other, what that means for the pi system is that those p orbitals that make up the pi system are also all completely aligned, okay? And if they're all in phase interacting with each other, that means that the electrons in that system have access to all four of those carbons, not just the two isolated p orbitals that are making up the individual double bonds. All four of those p orbitals can overlap and align so that those pi electrons in that system can interact with each other. Okay, and so that's sort of the crux of what's different about conjugated dienes. And so on Wednesday we will spend our time talking about how this arrangement affects the reactivity of conjugated dienes. Okay? So that's what's coming on Wednesday. What we're going to talk about right now is the reactivity of isolated dienes. And this part is a bit of review because essentially isolated dienes react like regular old alkenes. And so that's convenient. So if I have an isolated diene like this one that we've started with, and I try to do one of these reactions that we kind of beat into your head in Organic 1, like the addition of HBr, for instance, and if I add enough of that HBr, I can convince both of those alkenes to react as I would expect a normal alkene to react. So I would end up adding HBr, following Markovnikov's rule to that alkene, and I would do the same thing to the alkene on the left. And so I can do the same thing with all the other reactions that we've talked about. So if I use chlorine with this thing and I throw in enough chlorine relative to the amount of alkene I have, I can convince both of those alkenes to undergo a chlorination reaction. All right, so the take-home message here is that dienes that are isolated from one another, they react just the same as regular dienes. I just have to add in regular alkenes. I just have to add in more reactant to consume both of the double bonds. So that begs the question, what would happen if I took this diene and I carefully controlled the amount of Br2, for instance, that I added, or carefully controlled the amount of HBr that I added? So if I have one equivalent of this relative to one equivalent of that, I've got one double bond that's not going to react. So in this case, what I could do is I can actually react one of the double bonds with bromine and leave behind the second one. So I can actually get what we would call a multifunctional compound where one double bond is consumed, the other one stays behind. So I mean, I could do the same thing with, let's say, for instance, hydroboration. If I carefully control the amount of borane that I add in that system, and then follow that up with my workup from a long time ago, I can actually react one of those double bonds in the way that we would expect and leave behind the second one. If I were to carry out that reaction with excess borane, I would actually hydroborate both double bonds. But having more than one alkene that's isolated from the other allows us to do this scenario where we can actually get partial reactivity if we control the equivalence. Now, this example is unique in that both double bonds are equally substituted. What happens in a case like this, however? What if I had a system like this where one double bond is more substituted than the other? What happens in this case is we actually can get selectivity when we control the equivalence of the reagent. That more substituted double bond is also more electron rich. And what that means is it's more reactive. So in cases like this where the diene system is differentially substituted, if I carefully control the equivalence of the material that I'm reacting it with, I can preferentially react one over the other. So I would expect to preferentially react the more substituted double bond exclusively and leave behind the less substituted double bond. So I can actually take advantage of these differential electronics in the more substituted double bond versus the less substituted double bond and get reactivity to occur exclusively at the more substituted double bond. So we can look at other examples of this. So here's a system where I have two isolated double bonds. They're not in conjugation. And let's say I want to do something like a reaction we just talked about in the last chapter, an MCPBA epoxidation. I'm going to preferentially react this double bond because it's more substituted. So in a case like this, if I were to add only one equivalent of MCPBA, I would expect to preferentially epoxidize that carbon and leave behind the less reactive, less substituted double bond on the other side. Now all bets are off if I throw in enough MCPBA, right? Because remember, we're just dealing with rates here, relative rates. If I throw in an excess amount of MCPBA, I can react both alkenes. And so I would actually get this, what we would call a di-epoxide. So it all depends on how much material, how much reagent you add relative to the diene system that you're trying to react. But again, this is for isolated dienes. Let's do one more example. And I don't know, why don't we do HBr for this one? Okay. So again, I have to just look at the number of substitutions on each double bond. The double bond here on the left is going to be more substituted. It's a di-substituted double bond, so it's more electron rich. So that will be the site that will govern the reactivity if, again, I control the equivalence of that reagent that I'm using. So if I only add one equivalent of HBr relative to this system, I will hydrobrominate that double bond and leave behind this one. Okay, so it really has to do with recognizing how much reagent is there and which double bond is the most reactive of the two. All right, so that is as far as we got with the diene stuff on this Monday, so you should be all caught up now during your absence, and we'll pick up with reactions of conjugated dienes in class on Wednesday, and I will see you there.